In calculus, one of the neatest things that you can do is find the volume of an object when it's created by a function that has been rotated around an axis. So for this problem, we're going to take a look at the region that is bounded by a function and some different lines. We're going to rotate that around the x-axis and then find the volume of that shape. So the function that I have that we are going to rotate is y equals e to the x minus 8, and this region is also created by a few other lines such as y equals 0, x equals 8, and x equals 9. With a problem like this, probably one of the best things to do first is actually just create a graph of the region. That way you get a good idea of what is being rotated and what it looks like. This will be especially helpful for figuring out our bounds later on. So let's start off with that function, y equals e to the x minus 8. We can see that it's an exponential function, and the minus 8 shifts the entire thing right 8 units. So normally an exponential function starts off nice and small, and then usually it grows pretty quickly. For a normal exponential function, we would expect it to go through the point 0, 1, but since it has been shifted to the right by quite a bit, it will actually go through the point 8, 1. So I know for sure that that is a point on my initial function. Alright, now let's draw in some of the additional lines here. So y equals 0 is a nice horizontal line right on the x-axis. Consider that guy like right here. It looks like we also have one at x equals 8 and x equals 9, so those are vertical lines. Put one right here. And maybe another one right here. So 8 and 9. Now what this shows is that we have this nice little bounded region right in here. In fact, I'm going to color that in. So it's this region that is being rotated about the x-axis. Cool. Let's see if we can draw exactly what that looks like. So what we could imagine is maybe that first point gets rotated around, creates like a circle, and then since the function is bounding it, it opens up much like a lampshade, and then the outer part also rotates around, so it looks something like this. Alright. Now, the important part about graphing it out like this is we get a good idea as to what the slices look like. For this one, if you were to take a general slice out of it, it happens to be a circle. And that will happen no matter where we take a slice between 8 and 9. It will always look like a nice little circle. So when we go to set up our integral, we'll be looking at all of these circular slices and looking at them from 8 to 9. Alright, now that we have a good idea of what we're doing, let's go ahead and set up the integral. So for this integral, we'll be thinking of starting with the general formula from a to b of pi, our radius function, squared dx. Alright, so to get a sense of why this is working, this pi r squared is taking care of those circular slices, and we're moving through a and b. These will be our bounds from 8 to 9. Now what is really controlling our radius in this case is that function e to the x minus 8. Let's put that guy in. So pi, this will be e to the x minus 8. Whole thing is being squared, dx. Alright, so now that we have our integral set up, it should be fairly automatic from here in terms of just finding the antiderivative and plugging in our bounds. So let's do that. One of the first things I like to do with any of my integrals is, of course, pull out any constants, like that pi. I can also see that my function is raised to the second power, so I'm going to distribute that 2 into the power. So I have e to the 2x minus a 16. Awesome. Alright, so it looks like I need the antiderivative of this guy. And right now it's not entirely clear what that antiderivative is, but with the u substitution, I bet we can make it a lot more clear. So let's call u equal to the 2x minus 16. That seems like a pretty good choice for u, because then I'll end up with an e to the u, and finding the antiderivative of that is nice and easy. Alright, so if this is my choice for u, then du will be 2 dx. This will help me swap out the dx on the end of my integral. Alright, so moving the 2 to the other side, so dividing, I get 1/2 du equals dx. Alright, so from this u substitution, we can rewrite our integral. So I have pi, the integral of e to the u 1/2 du. So notice how I've taken out the 2x minus 16, it's now our u, and I've taken out the dx, it is now our 1/2 du. That's because of our first and our third equation here. Now when you do u substitution, with these definite integrals, it's also a good idea to switch out our bounds. So if x equals 9, I can imagine it being plugged into here, so I'd get 18 minus 16, or that u is equal to 2. Doing the same thing with the 8, I would have that x equals 8, plug it in here, so 16 minus 16, u is equal to 0. So now I have a much simpler integral to work with, and I can use that to find my answer. Alright, let's continue on. Looks like I've picked up another constant inside my integral. Let's go ahead and move that out and give it to the pi. And now I just need to find the antiderivative of e to the u, du. Perfect. Of course, e to the u is one of our favorite antiderivatives. It's just e to the u. Now we'll plug in our bounds, starting with the top one and then the bottom one. Alright, so we're pretty much done. Now we'll just simplify this as best as possible, such as taking care of this e to the 0, which is simply 1. And there you go. This represents our volume of our rotated object. So 1/2 pi multiplied by e squared minus 1.